Good morning, everyone. Thank you very much for taking time on Saturday to come here to attend this talk. So today I will be talking about the advanced observability strategies that we are using at Netflix in media processing space for media workflows. Since often observability is something thought as like once you instrument things, they just work, which I'll try to push it a little bit and show how when it will not work. So with that, this is a very familiar picture for all of you, I think. So this is from the season 2 of Squid Game. So you may be all binge watching the season 2 when it is dropped, but without knowing that there are millions of spans and thousands of microservice calls that are happening behind the scenes to encode a single episode of this season. And the same goes for any content that is like at least 1 hour run length. You would see like there is so much complexity that goes on behind the scenes to encode a title so that you can play back on all the devices. This episode can be played back on all Netflix supported devices. So which I will show in the numbers. I took exact numbers. So for that one episode of season 2 of Squid Game, we produced 140 video encodes. So that which includes multiple profiles, multiple bit rates under each profile, so that if you're watching Squid Game in your morning commute to office in a metro, you can still watch it on a low bandwidth, or you're in a big 10-foot TV at home, you can still watch it. So to support all of these, we produced 140 video encodes for that one episode. Similarly, coming to audio, it is 552 audio encodes that are produced for this episode. And that means a lot of compute. So I took the numbers and added them all up, and it took about 122,000 CPU hours to produce these 140 video encodes and 552 audio encodes. Now, coming to the focus of this presentation, observability, and it took roughly about 1 million spans to represent the workflows that are used to produce those encodes. And it involved approximately 27,000 microservice calls that happened within our media infrastructure to produce these encodes. And those microservice calls are serviced by 30 distinct unique microservices, which each has its own responsibilities of like audio, video processing, and text processing. So that's in terms of numbers of the complexity of encoding one episode, about approximately 45 minutes to 1 hour runtime. Now imagine at Netflix scale, we have like a wide variety of content of different run lengths, different quality profiles, animation content, action, different languages, different territories that we support, and ads also. Netflix also support ads in some geographies. So all of this media processing and also the encoding that happens before in the movie making process. While the daily video is shot, as a director want to see the content that was shot yesterday on 10 cameras, there is some video processing that has to happen so that everyone in the set can watch next day, like reduce the quality so that you can easily play back. All of this encoding is powered by the compute and storage fabric that is powered by our workflows. So that just paint a picture of complexity and variety and a lot of unpredictability that you get to. Sometimes we get given like a 11-hour, 12-hour content. I forgot what it was, some Nordic show, some TV show where there's a cruise going through some river, and it's like a 12-hour content that was given to us. Even the ads are like 30 seconds long. So there are different types of content which we support. Now with that, about me, my name is Naveen. I'm a staff software engineer at Netflix, and I work at Netflix Warsaw engineering office. I have been at Netflix for about 11 years. and I moved to Warsaw temporarily for 2 years to set up engineering office here, like presence for our team here. And I've been here from last 8 months. I'm loving it. And Netflix, how we connect into the whole engineering, how we the work we do, it connects like this. Where like Netflix Warsaw Engineering Office, we have multiple teams in Warsaw Engineering Office. I'm from the first one, which is here content and business products engineering. A part of that is media infrastructure, encoding infrastructure, which I'm part of. And there are also other teams, and there are more and more always coming up, like games platform engineering, games lifecycle engineering, infrastructure engineering, data engineering, and also like the member engineering, which is more close to product, like things that happen when you log in to the product in that space. So that's just a sampling. And coming into my own team, our mission is like to provide the media infrastructure platform and to keep on track with like the advancements or the newer things the business is trying to do. Ads is a recent example, like from 2 years ago or 2-3 years ago, when business wants to do ads, which is media processing, that came to our team, and that's a challenge that we work on. Similarly, when there is a content, like we're venturing into new content profiles like live recently, the SWOT encoding is also powered by our infrastructure. So I'm in this team in this content business products called as Content Infrastructure Solutions, which has a wide variety of things, not only media processing, but also things adjacent to it, like metadata management and studio workflows. All these things are managed by our team. We produce infrastructure and solutions services which power that part of business. So for today's agenda, I will share a roadmap on the observability challenges and how did we evolve it in the media processing space from a very basic one to all the way to like more advanced versions. And yesterday I was here in the same room. I think it was Sebastian or someone who presented like an open telemetry talk in the same slot. So you will be seeing in this presentation, I will be making those references, which was very connected with our work. We use quite a bit of open telemetry for this observability in our workflows. Then I'll talk about evolution, then quickly wins and what is still yet to be solved in the future for us. To set the stage, I quickly will go over like the process of encoding itself. This is a super simplified version so that there is some stage set up, then we can use that to discuss and you can appreciate the complexity of observability. So here what I'm presenting is video encoding, where to encode one video, that is the 140 video encodes that I presented before. If you take one of those, that is the one I'm double clicking into and presenting here. So this is a very high level process that happens to encode it. First, we get a title from the studios. That's the ingestion process, which has storage and upload. Then there is a most compute intensive operation, which is encoding. Since it is so complex and iterative and needs a lot of CPU, obviously you do divide and conquer, which is we split the work on time axis in fixed time chunks, or sometimes we chunk by scene complexity. Example, if there is some intro where there are titles, it's not as complex. If there's some action sequence going on in the movie somewhere, that's more complex, which needs more processing so that we can produce optimal encode. So the chunking of the video happens based on time, fixed time every 2 seconds, 30 seconds, or based on scene complexity. And then each of those chunks is encoded and assembled back. Then that produces an encoded video for one profile, one bitrate. That is one of those 140 encodes. Now it has to be packaged so that the raw encode itself cannot be played back on the players, HTML5 player or any of the VLC, any popular players. So there are standards for the packaging formats, which will be used to package the video, then also pulling in audio and package it so that it can be played back on the devices. Then the packaged content is deployed to CDN. Netflix has our own CDN called as Open Connect, which has been there for like more than a decade plus now. So we deploy this encoded packaged video to CDN. So that's a very high level of the process. And there is, in the encoding space, the second step. There is also iterative step, which I did not show for simplicity. But there are cases, just for information, if the encode that is produced, sometimes what we do is we iteratively try to encode it one more time, second time, third time, till we can squeeze and compress the encode more and more. So more compute we spend upfront on the server side. On the device side, you will have a best experience using less data and more better quality. And you don't have a hot phone getting hot when you're when you're commuting and all that. So that's why there is even more number of times where we do that split and assemble, like sometimes 5, 6 times actually. So now how do we do it? For this, we have media processing infrastructure platforms. At least in 10 years, I've been at Netflix now, I've been in the same domain. We are on third version of media processing platform called as Cosmos, which we have blogged about a few years ago, which has a lot of details on the internals of it. So at a high level, what happens is there's a Cosmos encoding platform, which all our users from encoding technologies, who are the experts in audio, video standards, text standards, color science. So they are our users who build these microservices, which is a box in this picture here. And then that is how the whole encoding works. So what you're seeing here is again a simplified version where I'm showing 3 levels of microservices that our users have created using Cosmos platform. On the top is like Tapas is one encoding service, actual encoding service, microservice. Then Sagan is another encoding service. So Tapas powers all encoding for playback that is on the main Netflix product. That is when you click play on a movie or a series, the encoding, the playback for that is all taken care of by Tapas, also ads. Sagan is for more in the movie making process of producing proxies, generating a different version of encode for dubbing artists. So those internal studio use cases are powered by Sagan. But what you see here is that the second layer has video and audio encoder. Both Tapas and Sagan share that. Since both of them need video and audio encoding. And if you go further down, you will see more and more reuse happening. So imagine this is like a skyscraper where you have the bottom floors, the foundations have to be strong. Then you can easily build the top floors. That's what goes on here. In actual encoding case, like for Squid Game example I've shown, you would see like 7 layers. I couldn't fit that in the picture here. I'm only showing 3. So that is a level of complexity. And each of those boxes, which is a microservice, has an API workflow to keep track of state, since encoding can take a day sometimes, few hours sometimes. And then there is serverless functions. So combination of API, workflow, functions put together makes one box. So that if you click into each of those boxes, you would see that. So all of that encoding platform is again from our team. So now we'll get into challenges of observability. So the platform itself, when we started back when I was like in 2014, we had a monolith. Then around 2016, there was a better monolith, a larger monolith, like the one you see there. Since it's mostly about engineering capacity, resource constraints, we are like 5, 6 people. Due to that, monolith gives us more agility, like that's all we could do. And from there, at one point about when we were at 2018-17 timeframe, this monolith was not working since more and more users were using the platform. And oftentimes we used to make changes once every month and all that. So from that was not sustainable. We want to let our users do CI/CD and all that. And this monolithic architecture was a big hurdle blocker in that vision. So then what we did is in 2017-18 timeframe started doing microservices and breaking down the monolith, which is in a simple way like 2 layers like that is how we started. And soon we realized why can't we go all the way? Then we started more layers. then even more like that. And today, if you take a picture, you will see 7, 8 layers too. So that is how from monolith we went to distributed microservices-based architecture and indexed even heavier into distributedness. So what you see is the complexity. Again, the other angle of complexity is within one of those microservices. If you look at it, I tried to draw the steps that happen within Sagan workflow, one of the top level services. It's like very confusing. Literally, you will see like very cyclomatically, like they talk to each other and all that. So this is what I could draw. You don't have to read through this, but I'm mostly trying to tell the complexity that you would see if you peek into one of the boxes. So now challenge is, imagine like what would take to get observability into this. If something fails, how do you quickly provide a way for our users to find that needle in the haystack so that they can quickly restart it or push a fix or something like that. Also, this is the one I was talking about. Now, on this top of complex hierarchical services, users would like to drill down when there's a problem. Generally, our users get complaints, or they will be coming against in their production environment. Like someone in a 2011 version of a Blu-ray player somewhere in Asia is seeing a green frame at 11th second, for example, in their movie. That's all. That's all they get. Okay. Now, from that, they have to drill down and should be able to find out is that which part is contributing to that, and when was that change happening, and all that. Is it widespread or only affecting one profile, one video encode, all that. Also, proactively, our users want to surface errors, more enriched errors with context added at every layer. And any milestones they reach in the encoding, they want to surface up so that they can see progress in terms of milestones, not like all the steps, since it's a lot of information. So we also have to support these two dimensions of information flow in our architecture. Now, another dimension, this is for one of the top level service. I think it's Sagan or Tapas or Sagan, one of them. What I did is, I went into our observability tool, which I'll talk about more, and opened up all those microservice calls it has made to encode one title, the same Squid Game episode. So here you can see each of those red or green pill there you see is like a request. And from one service on top level, it has made so many microservice calls to encode audio, video, package, and all that. I had to scroll and take screenshots. And that is a fan out happening at one layer. Now imagine, like same fan out happens at every layer down below. Other dimension of challenges we see is in the traditional systems, you have to support by using three things. You would say logs, traces, and then that gets to domain data. We have to support bidirectional observability navigation for our users. By keeping traditional things on top, we have a notion of request, which is added, which we'll talk more later. Also, we have to support the reverse direction when the green frame example I've shown. When there's a problem, that's all the users have to deal with. And from there, how do they come up to the request or a build or a code change? So we have to support this bi-directional debugging flows in our platform. To compare here between like the traditional and the media processing environments, so you would have like the workloads, the typical workloads you see in observability domain outside, a lot of literature is about microservices, but our workloads are all batch. Since all of encoding takes hours, so you cannot have a microservice waiting for hours, right? So it's all async and batch workloads. Due to that, it will be like the work that is submitted from a top level service may be executed like after 5 days. So there's a long wait period due to like with a purpose. So we have to represent that. So that's how our workloads are a little bit different. And then for the metrics, everyone knows about low cardinality metrics, which is the cardinality is the number of tags you would have in a metric. We have that. Plus, we also have high cardinality metric. Again, going back to the example for our users, they want the metrics we emit in the platform to be decorated with more rich information, like the profile, the FFmpeg version that was used. So these all make high cardinality metrics, build IDs, commit hash, generally, which is expensive to store for longer duration. And then namespaces also, due to hierarchical nature, we have like hierarchical namespaces which are connected to each other. The owner of the microservice in our domain, when they're working at a layer, they want to see the logs and metrics in their microservice and down below. They may not be interested in the things that are up top. So we have to support the navigation capability and also allow the owner of the microservice to zoom in. And coming to tracing, tracing is not optional in our space. All traces are required. Since I'll share more later too, like we are using tracing in our platform as a must-have to connect all these layers of microservices. In fact, like a lot of debugging workflows or operational insight starts with a trace. So we cannot do sampling. We have to have all the traces for all the requests. Without that, none of the tools work for us. So that's like summary of the challenges of doing observability at scale for media workflows. So monitoring asynchronous task is one, and then we'll talk more. As I mentioned before, there are 1 million span counts. So would general deployment of OpenTelemetry system work, or what happens if you have, then that's only for one episode, but you have more and more movies coming in. You have millions and millions of spans produced per hour. And also decorating trace data with high cardinality, and also reasoning the encoding latencies, which we'll talk more. Since the users also come back and say, after all the observability is available, then they generally come and tell, why is this encode taking 4 hours? What can I do to cut it by half? So that challenge also we'll see. So how did we evolve to meet all those challenges? We went step by step by unlocking value at every level. So first, monolithic architecture, mostly up until 2018. From there, we went to distributed architecture, and then I'm not able to see here. So, but also the real-time insights, and then business insights on top. So kept on evolving like every 1-2 years as the first level of challenges are solved. Then we started using the platform to get more information out of it. Next, where we are right now is connected data. So here you would see timeline. That's generally the timeline from 2019, 18 till 25. So roughly 1 to 2 years, we've been working through these challenges and improving our platform. So in the distributed async architecture, which we have seen before. So what we have here is to support all the requests and logs, all of this correlation and the breadcrumbs, how do we connect them? So everyone thinks like once you go distributed, it solves a lot of problems. It solves definitely for the scale, and also like to support, to reduce the blast radius of the issues, and everyone can release the changes independently. But then observability proportionally got complex and complex, especially go lower with hierarchical services, you go every layer down, it even increases exponentially actually. And debugging became that much harder. Definitely everyone, you would see generally in 2019, 2020, you see like everyone has a lot of Chrome tabs open to manually connecting all these dots. And then performance and wait times. Since when we use queues, all the arrows that I've shown in the previous picture, for reliability and to have this asynchronous nature provide in the platform, we use queues for all those connections. So when you have those many queues, then you will have waits, And sometimes wait is desirable since there is no compute available. Since we always have more work than we have compute resources available at Netflix. It's always the case. That is like the basic thing. It's not it happens only seldom. It is every day the case. So that means we have to work on high priority work, which is the movies and titles that are needed like tomorrow or yesterday or like in a week. Anything that can go live or that will go live in a month can come later. So that means it is totally valid by design to have work part. So that kind of wait is different. But if there is a wait happening between each of these steps due to some missed connection, missed metadata correlation, that is not desirable. So now our observability tooling should be able to answer which one of those, or the wait is due to which reason. Is it due to a planned like backlog, or is it due to something going wrong? And traditionally, everyone has a three pillars, which is very nascent where we were 2016, 17. But definitely for us, we have to go beyond. We'll see more. This was not sufficient for us. So we use OpenTelemetry. Again, this is first thing we started was the 18 first monolith to microservices-based distributed architecture. We had functional solution working. Then to put it all together, we started using OpenTelemetry. Maybe OpenTelemetry came along a little later, but we had some other distributed tracing mechanism that we were using. But overall, distributed tracing is what we started using. And then OpenTelemetry came along, then we started using that one. And Zipkin, we use Zipkin-based trace models. And then other one was like after tracing, we were incrementally like seeing the issues. After using OpenTelemetry and then Zipkin, the view that is presented in Zipkin default UI was not meeting. For one is our scale due to the number of events. Other is also for async workloads, the instrumentation there is something that is missing. Like it does not show quite a bit when there is a work is parked. For that is not shown like quite the way we wanted. Due to that, we started the journey of having our own visualization tooling. So this is the sample from early version of internal visualization tooling that we built. So what you're seeing here is like maybe one of the third or fourth layer microservice. Since when you go lower services, you would see less number of activities going on. You go to higher levels, you will see more orchestration. So what you're seeing here is like a flattened out structure of activities happening within one microservice call. And here you can see the light color. All of this data, this representation is inferred from the underlying tracing data. Just we're presenting it in this way, which is convenient. In the mental model in which our service developers build the services, we are matching it. So that we are showing wait time here, and also we show the darker colors show the processing time. These are generally clues for any unexplained wait, unexplained regression in performance regressions. So this is the way how users would approach it. And then, so we just had this, means looking back, we can say these all things have to be connected, but when we were starting, it was always like kind of firefighting or quarter to quarter. We were working to get the distributed architecture we have out there, to get it to live and fully cut over from monolith. So due to that, we were doing just enough things to get our distributed architecture flying. And then what happened is the basic visualization and all that worked fine. We had first some workflows of Sagan, which are a little bit simpler than Tapas, which were what were used to verify the functionality of Cosmos. Later, we onboarded Tapas, which is a more complex workflows. And then we started seeing scale. The number of microservice calls and the numbers I presented before started coming in. And then a lot of issues. Examples were like this. We had cases of more than 300,000 spans per trace, one trace. So one trace is like encoding one movie, basically. And there were, again, as I said before, like traces running for days. It is running in the terms of tracing world, but they're all parked in the middle due to unavailable compute. Or if it is a lower priority. For example, if there is an encode, the scenario where this happens is if we're doing a campaign to catch up a bug in an encode, we want to re-encode all affected videos. Sometimes we re-encode like maybe movies and titles which have highest view share. The other titles which are low view share, maybe we'll re-encode them opportunistically. Since re-encoding all of that upfront may not be a good choice. So due to that, also sometimes you would see this waiting of days, even weeks. There are hundreds of thousands of requests, which translates to number of traces. So then everybody started seeing these. Generally UI, definitely. When you try to open a trace view, nothing renders. And then also everyone waiting at every step. You were looking for logs, you had to wait, you had to answer some question on why there is a problem, logs, and all the data that the vision that we had that used to land after 10, 15 minutes. But by then the heat is gone. Like users generally SSH in, they're very super frustrated. So that's what we were facing with immediately after when we went with a larger scale. So that view looks like this. So when scale hit, this is a sampling of, again, tapas, top level service, if you follow through the labels on the left. So these are the trace visualization tools were showing this to our users, and all the reds or like maroonish color, those are like retries. All of these were coming in. Pretty much this data like was hard for users to even click through and reason. Now we thought there is observability, but they're like not sure what to do from this. Like the middle red, the large red bar there, like is it optional thing or is there anything else that is dependent on it? Can I retry, not retry it? And how much compute would I waste if I retry? All those things they were not able to answer from this. So this is what was happening when we were hit with scale. And by the way, that was scale for our platform, but that's very normal business since encoding movies is the main purpose why we built Cosmos. So then what we did is, by most of this firefighting and all the user feedback sessions or watching the users over their shoulders, what they were doing is definitely the person who's chasing the problem would discard all the noise, and since they know the domain, they will be identifying span 1, span 66, span 10,000, span 20,000, and done. That's all they trace. They don't care about all of the things happening here. So from there, we just observed, okay, that's a aha moment. Like that's all in the mental model of that one engineer, the service operator, that's all they care about. So trace is good, spans is good for one purpose, but when the other dimension we need is requests. So on top of traces, each flow from start to the tail end is a request. So we introduce this notion of request. So every time a top level service sends work, it creates a request ID. And still the previous trace notion is still there, but now on top we added request ID as a decorator to traces and spans. And then we thought that is sufficient, but was not. We took even further. The lower level microservice, in this case second layer, when it calls its downstream, it also creates another request ID. So pretty much you see like something like traces having parent span, child span. We have a parent request ID, child request ID, root request ID. Root request ID is the top one here. So we have request every time a microservice calls another microservice, there's a request ID on top of tracing and root request ID. Then this provided us another view where from this trace data, you can take a request ID and then only collect those spans and create a collection, which generally makes sense for easy to digest and it scales. Since how much ever how many ever activities we do for encoding a whole title, but when you're debugging or like modifying a request flow, you're only dealing with that much of complexity, which is generally does not become 2x and all. So that's how the request concept was super helpful. Then we started using the notion of request also to build request adjacency list, which is overall in the graph to connect to the lower level request to the root request. So this was super helpful, and request IDs were connected to spans. Now this is the other view of that previous trace view, which has a lot of data which is not very useful. We're presenting same data in our tool with requests first view. So you see on the right, generally there are also some filters on the top which are not shown in the screenshot. User of audio encoder, when they're debugging a problem, they would filter for audio encoder and click on it, send like 500 requests. They would filter by profile or something, click on that request and just debug that flow. So this is an additional view we added, which is derived a little bit from request adjacency list work. It was okay, but still we had issues and scale challenges. Even with that, means for some workflows we solved the problem of slowness, since kind of if you look at it, we avoided solving the actual problem of lot of spans and traces. Instead, we said you don't need so much data, just take one request, right? That is how we were able to unlock value with the previous work. But still, someone want to see aggregate. For this total movie, if we have to encode, take out all the weights, where are the longest weights? And how much compute are we spending in retries? How much money are retries costing? Those things, to answer them, we need the aggregate picture, which means hundreds of thousands of spans. We have to pull them together to analyze, which was again, we're hitting at these challenges. So then what we did is just change a little bit, moved from traditional tracing usage, and what we did is move to this model of individual spans. There is a notion of trace, but in OpenTelemetry, we're not quite literally connecting all the spans to this trace. Or other way to see it is, each of this work that is happening is a span, and there is OpenTelemetry connection also there with trace, parent span, child span, all that. But in our systems, we were only using span notion and connecting it with a different dimension, request ID and some other metadata about the encode. So with that, we were able to answer, means the data became kind of flattened out, and we were able to get more answers from by presenting data like this, which we'll see more request wait times and even more filtering. Like we don't have to, with this model, we don't have to mine the data stored in OpenTelemetry and then do this filtering. We were able to store this span separately ourselves in a different data store and get these answers. And we're able to aggregate and all that. So with that, we were able to give this kind of higher level aggregate metrics to our users, which is, if you look at the previous pictures, like where spans were all flattened out. Now a span of type encode VP9, for example, is a flat record. Like it is part of a trace, yes. But now our data store, the way we stored, allowed us to compute P99, like P80, 95 for that one span. So we were able to give this different kind of aggregate metrics for our users, which is what they were looking at. So which is now transitioning from observability into more efficiency optimization and some business value unlocking. That's what was going on. So that's the kind of value. Another view we're presenting in our observability tool to our users to tune their workloads. Still, there were challenges to produce this data. It was taking still a long time. Mostly if you do pre-compute, like do analysis, like in Iceberg and all later, like after a day, it was fine. But if someone wants real time, we were having still issues. with slowness. So as we can see now, quickly pause here. We were at monolithic architecture to distributed. Then distributed had observability issues that were solved. Then we did scale problem, solved that. Now observability was pretty much working fine. Now users are using it for business insights, telling to the business saying that, hey, this movie, it needs so many hours to encode. We cannot go any shorter than that. They're confidently able to tell that. That's where they were. But now the users are like, I want to tell that or get those insights right then, not like after one day. So they want to see this aggregate analysis, data also real time or near real time, maybe few minutes of latency is fine, but not hours. So how did we approach it? As most of you must have guessed, there will be some eventing that we'll be using. So piggybacking on this individual spans model that we had, we embraced the streaming model. So overall, what we see in this picture is here on the left, those are technical things we thought we solved, but yes, we did. But from that, there was this business questions that people started asking, like system level analysis, or like how many such requests were there, or even am I meeting SLOs? So like higher level things are being asked from this data. Which all of them, if you look at them on the questions, they all need aggregation. So we have to aggregate, which we were like mostly doing as a post-processing after a day. So then what we did is took these traces and spans and started emitting them as events into Kafka Stream. So we use so stream processing is how we approached it, and then we were able to kind of pre-aggregate or aggregate the data as it was coming in for the top 10 queries or top 5 queries that users were asking us. So roughly you can see, if you put a lens into this and see, you will see like a lot of these events, Kafka getting a lot of events. And then we use Apache Flink to create a span event processor to aggregate and to address the top 10 queries that we had. So that's how we extended spans from observability all the way into business insight, real-time business insights. And then those aggregated data, which we stored for faster access to Elasticsearch, standard stuff, and then also Iceberg for trending. Since there's also a use case which comes in after users have this top 10 queries, they also want to see what is trending of that metric over like a 6-month period. Is encode getting better or getting worse? Or is there footprint or the size of encode? What is happening? All of that we put into Iceberg for that analysis. Now, more interesting things we were able to do with this, most of the work from having individual spans is where a lot of value is unlocked. With real time, also some extra layer of value for this use case. Here, the problem we are going after is what is the best case processing latency, assuming if we have infinite compute and all the queues, there is no weight in all these connections between the pipes. So to do that, this is the kind of analysis that we produced, and this is a visual depiction here for presentation. The height of each of this step is how much time that step takes. As you can see, video encodes would generally be like more taller since more compute intensive. And the edge, the length of the edge is the queue duration. That is how long the work was in queue before it was executed. And it is in queue due to different reasons, maybe due to dependencies or due to priorities and all that. Now, once we have that kind of representation of the graph, then we're able to answer very interesting data that our users wanted, which is what is the best case processing time that we can get for this workload without tuning what is going on inside the boxes. Obviously, if you have an encoder that is like 2x faster, that is one way to optimize. But the problem we are looking at is keeping the boxes as black box. what can we do in the workflow can we change the steps, change the order in which we do. That analysis is what we're able to do from this data. So basically, if we are able to present this one, no queue wait times, and if you look at this one, the longest path, I think, we'll see in the next picture. I'll show that one. But if you can see here, the video encode and the assemble and the package, that step takes that long. If you take audio encode, which is on the right, even if you tune the audio encode, it's not going to help much, since the longest processing, long pole here is video encode. So without tuning that is how best you can process the movie. And all other things that are happening around audio, text processing, they finish well within video encoding time frame. So this data we were able to present, and this helps business and our encoding technologies users to focus on like the right area if they want to really cut short the end-to-end processing of the movie. In math, like these numbers are what we were presenting. The total processing time is from the first span till the last span. This number we presented, we're able to compute in real time. And best case processing time is like without any queue waits. What would that number be? By taking all the weights. And then how much time are we wasting due to queuing is the other way to see the data. Total processing minus best case. So effectively, we were able to present to them, distill the whole problem down. If someone who's want to optimize the work end-to-end processing, that's what they should go after, the red path there. And this has helped quite a bit in, means again, those are hard problems to solve, but like it helped in our users to prioritize their work. I think we talked about this. So this is the long pole I was referring to, which is in the red here. And the other thing we were able to do from this data is the data that I mentioned before, for our span processors in real time, we're doing some aggregates and storing into Elasticsearch. From that data, were able to kind of use that total processing time, wait times, metrics, and do some P99, do some SLOs, alerting, all of that we were able to unlock, mostly near real time, which was like unheard of before for our users. They were mostly like reactively looking at if encoding should just finish within 5 hours, just based on empirical data, but no science or no backing data before, versus now, there is data and also alertable. So business insights, a lot of happy customers, happy users. So more business insights is what we started going after. So engineering questions, slowly, the trend, that is a continues to be trend last 4 or 5 years. More and more, we're trying that to business. The recent trend is like SLOs. Also, the other one is cost. Now since we have this kind of data for instrumented, we use the same one with all the processing blocks. We are able to attribute a cost, since by using some average compute costs and storage costs, we are able to answer to the business what is the cost per movie. Even very interesting, cost for redeliveries. If a studio redelivers a movie due to maybe there is some error somewhere, they just redelivered, how much did that cost to us to re-encode it? Or should we re-encode the whole thing, or should we re-encode only what was redelivered? So those all numbers, once you started putting these business numbers out, it became very easy to optimize. Also the cost of production house and all that, we were able to answer. So then, like to evolve, to scale this even more and make it more self-sustainable, what was happening is, since trace analytics were used a lot, so we started using trace analytics plus the another dimension we added, which has been going on, but they were never merged, which is users in their code, they emit metrics. Just like when they reach milestone in their encoding steps, but those two islands all along. Then we embarked on this journey since there are more value in the metrics. So metrics and trace data, we found some common points and started processing them together. So we extended our, this is some mechanics to make it easy to emit the metrics. We published a metrics client, and then everyone used it to emit the metrics in a consistent way, where that all the metrics have required tags. This is independent from the tracing data. Then we were able to send all of those metrics also to Kafka. And since all of them have required tags, also span tags also were added on the metrics so that we can go both directions, from metrics to trace, trace to metrics. So there's one more also here. Metrics is what user emits, and there is metadata, which is mostly like the thing that is the data available for all the jobs, which is not trace, mostly video profile and such things, which are common base instrumented data. So these three things, three streams of Kafka, we're sending into our processor, the Flink processor. And overall, what this led to is more rich and more projections, more dimensions is what it was outputting into the Iceberg and Elasticsearch. Example would be someone in Elasticsearch our user want to set up a dashboard that shows VP9 particular bit rate, what is the average processing time, best processing time. They're able to do it now. Previously, it was always video encode, best processing time. That's it. They cannot drill down further, but now they are able to. So that's the value we got by using more sources to enrich the trace data. So that's more in action, different kind of data coming together. And this is how we were like joining requests, traces, metrics all together. And also metadata. So what else? So these are just like more details on how the data is stored to different projections of what we output. And also we were outputting execution tree in like the long pole analysis that was derived from that data. That is also outputted from when we have the full data from start to end, a movie is encoded completely, we were outputting that also. I think, yeah, those are what we were able to do, all these things from this data. And so the wins were like connected data, since we connected metrics and metadata and the trace data. And there were still some concerns around like more connections. Obviously, which is where what keeps us busy now, which is like there's some more data sources. Like don't only look at when movie encoding phase. Can we look at some data that is while movie is being produced? Can we use some data from upstream also to know what parts of this encode would be complex ahead of time? So that kind of things are going on. And more other thing is you can expect like when there's so many assumptions we make that traces, metadata, metrics, traces should have some common keys. And when we give to users, someone calls video height as H capital, someone calls H, someone calls VH, lowercase height. So this is what we were started seeing once we published this metrics client to our users. Then we introduced the taxonomy service to have a schema so that anyone who want to emit a new tag and then which is business critical, then we had a taxonomy service where you have to onboard it, and then the metrics client has that schema will be updated in the metrics client, so that anyone who want to use height, publish the height value, they have to look up the schema. If it is there, just use it. Like don't invent another tag. This is a work in progress. So we put a taxonomy around tags. So this is where we are now. Happy so far, fingers crossed. That's more canonical model. So also there's some other types of wins that happened which we didn't expect when we embarked on this work, which is like after having all this data, some folks looked at this and said that, hey, here and here we're doing same video encode. Why should we do twice? Since we have all the data to tell that they're same, even with the SHA, with the request parameters are same, just reuse. That's called caching project, which was a simple work and gave quite a bit of savings. One of the color is trace cache hit and cache miss. So that gave us a bunch of savings. And more cost efficiency work that we did in different business verticals. And the ones which have shorter length means there's more efficiency. Maybe there's some unexplained wait times we have to go after, which is work in progress. The one on the top is like pretty efficient, which is all the compute is used for a purpose that we can explain. This is another projection, other view of cost. The y-axis is not shown for like keep the data privacy. The future I think looking at is, as I said before, more connectivity upstream, downstream is one big one. Other is federated GraphQL connects with the connected data. We have all these data sets, but keep the domain expert, but then allow them to connect. Taxonomy adoption, which is still proof of concept right now, and performance enhancements. I think that's it. A lot of slides. I'll pause here and take any questions. So means that is from a different team that we use service from. But what we there is a good. In fact, I linked actually here from David Gilda is from our central monitoring team who manages the whole. Infrastructure of logs, metrics, and all. So this is a very good presentation. Just look at this presentation has very good insights on that. So overall, we rely on them for solving the problem. And what we get is that do not worry about that. It is super cheap for value we are able to get by tuning encodes. This is negligible. This cost of indexing of tracing all the data is still fine. We're getting ROI, lot of ROI. So. Okay, you mean, okay. Question is basically, are we using request ID from OpenTelemetry, any feature in OpenTelemetry to use request ID or separate thing? Yes, yeah, 100%, yes. So generating requests, we are very intentional. Like some places we mark the boundary of requests is defined in our domain. Like every call is not a request ID. So due to that, there is a instrumentation we have done on top of OpenTelemetry in our platform to do that actually. Yes, on the spans we're using labels to add the request ID and the root request ID. So, no, actually we do use OpenTelemetry OTel collector still, but just the places where instrumentation happened. For example, I was there at yesterday's presentation here. Like if it is a microservice like SBN, a Spring Boot, you would use the default Spring's telemetry integration, but here we couldn't. Means the places where we start a span, close a span, those we take control. But the OTel collector, the machinery after, only instrumentation we took control, but like after emitting a span, what happens? We use from OpenTelemetry infrastructure. So, okay. Otherwise, I'm around, we can chat more. Thank you.